Good day, everyone. In partial fulfillment of the requirements for the degree of Bachelor of Science in Mechanical Engineering, this undergraduate thesis is presented to the School of Mechanical and Manufacturing Engineering, Mapua University. This thesis is titled Topology Optimization and Strength Performance Analysis of a Lower Control Arm Sedan Suspension Part. Now let me read to you the abstract of the study. The selection of an excellent vehicle includes the safety and comfort of passengers, which a suspension system provides. The suspension system of a sedan usually consists of lower control arms, coil springs, and struts. In a sedan-type vehicle, a lower control arm is considered as the most important part of a suspension system because this prevents the wheels from misaligning and separating from the vehicle body. The lower control arm being subjected in this study is a commercially installed lower control arm in a McPherson strut assembly on a Toyota sedan model, the Vios. In this study, the control arm models are modeled and simulated through Autodesk Fusion 360's CAD or CAE function and topology optimization techniques to reduce the weight and volume of the component. The strung and unsprung weights are considered as load cases to simulate the redesigned lower control arm model on a flat terrain condition. Static stress analysis is used to find the design matrix consisting of the percent weight reduction, deformation, yield stress, and safety factor on the redesigned model. I'm Brian Jones Monteverde, and I'll be discussing to you the first part of this thesis. Suspension system. Suspension system basically suppresses vibration, and these vibrations come from the different operations that we do on, let's say, driving a car or riding on a car. There are different forces that are acting on the wheels. So a suspension system is responsible for suppressing those forces or vibrations. We know that the suspension system consists of the springs, dampers, and mechanical linkages. These mechanical linkages are connected all together to create a not so sophisticated system that will ensure comfort and safety for the vehicle occupants. Here are the main purposes of a suspension system. First is to maintain vertical contact between ground and wheel. This is important for your car to keep moving. Second, maintain proper attitude during different operations, which includes turning or just cruising on a highway or subjected to, to holes in the road, all of those different types of conditions and operations. Third is the overall performance should limit spring displacement. So we are when the suspension system is subjected to loads, or let's say a bump in the road, it should limit the spring displacement because the spring is responsible for suppressing those vibrations. And the forces and maintenance costs should also be considered because the maintenance cost of a car depends on the useful life of a car. So basically, if we have a really bad suspension system, our car parts will be subjected to more vibrations. Thus, we need to fix it more often than having a good suspension system. Okay, so in a part of the suspension system, we take note of the lower control arm because this is the thing that we need to focus on in this study. It is the most important part for joining the steering knuckle to the vehicle frame. So basically, it is connecting the wheels to the car. It is responsible for that, and guides the upward and downward motion of the wheel and maintains wheel vertical alignment, like I said a while ago. So where did lower control arms originate? They originated from bird furcula or wishbone. This wishbone is located in the chest area of a bird. When they are mid-air and they are subjected to vibrations from the air flowing through them, those furcula act as suppressors of those vibrations. They need to withstand the rigors of flight, which is the same as a lower control arm. So this is where engineers got the idea of putting a lower control arm in a suspension system. So what type of suspension system we are talking about here? We are going to consider McPherson strut because this type of assembly is commonly found on sedans, and we are focusing on sedans here. In different types of vehicles, there can be different types of assemblies, but mostly on sedans, McPherson struts are installed in the front wheels of the car, and we will be focusing on that one. And also, we can see here in the diagram that we have the different parts of the suspension system. We have the vehicle frame, we also have the lower control arm in blue, and we have the steering knuckle that is connected to the lower control arm, and that steering knuckle is connected to the strut assembly. We know now that in a strut assembly, you can see springs here. We are really familiar with the coil springs here because they tend to compress and decompress over time because of the forces that are applied to the suspension system. So to be more specific on the type of suspension system that we are going to use, or the lower control arm that we're going to use, we will be focusing on the Toyota Vios model because Toyota Vios is commercially available in the Philippines, right? And we need to be careful on the weight on the weight that we need to consider this one. Based on our research, the gross weight vehicle ratio, or GVWR, of a Toyota Vios is 1,500 kilograms. This includes the chassis, the body, engine, and other stock accessories, but not including any passengers or any accessories that are installed afterwards. And it is important because we need this value for our computations. So let's talk about topology optimization and finite element analysis. Topology optimization is to figure out an optimal layout of a structure. The results of optimizing a design, um, it needs to it will result on a fine and gradient computation, meaning that these computations are really sophisticated that only softwares can perform these computations in a really short amount of time. So by optimizing a component, we reduce weight, meaning reducing volume. And we can achieve this using design variables such as applied load, support conditions, volume, and design restrictions that will be discussed more on chapter 4. Before we can we can optimize a design, we need to perform first a finite element analysis. We need this because it uses simulation method on physical phenomena using key mathematical computations. This addresses structural mechanic problems and quantifies deformation, yield stress, percent weight reduction, and safety factors. So basically, when we try to simulate um, the newly designed model, it will instantly give us values for this one. And it is important that we consider the finite element analysis so that we can see the load paths or the stresses in the certain parts of the component. Okay, for this, we will consider two types of load cases. We will consider first the sprung weight. So basically, all weight supported by the springs, coils, air springs, and etc. This will consist of the chassis, engine, body, and stock accessories. The unsprung weight, basically all the weight not supported by the springs when operated. We have the wheels, tires, brakes, drive axles, and other parts that are connected to the wheel. We can see the diagram on the right that the sprung weight is just basically any weight that is lifted by the suspension, or that is carried by the suspension system. And the unsprung weight, most of it is the suspension system itself. Okay. Statement of the problem. Constant load stresses in different parts of the component while maneuvering terrains requires an excellent suspension system. We all know that most consumers nowadays look for a certain car or certain vehicle that has really good suspension system because it can define the ride comfort and it can define the safety of the passengers that are riding in it. Understanding weight efficient and excellent suspension system, it is important to ensure the comfort, safety, and economical manufacturing cost. Because when we are performing topology optimization and finite element analysis, we can significantly reduce the weight and volume of this certain component, right? And the material that we can save by performing optimization, we can create another material out of it. So we can be more economical. We are not wasting material on unnecessary parts of the component. And most old control arm models are not topologically optimized. Back then, during the old days, we know that most car parts are just molded on simple molds. They were not. They were carefully computed, yes, but they were not simulated on softwares because of the technological constraints back then. Also, revising an existing design will lead to a topologically optimized new design. That is for sure. Objectives of the study. We have the general objective. First is to perform finite element analysis on a lower control arm. Second is to create a topologically optimized design. And third is to use Autodesk Fusion 360 as a simulation software. Going to specific objectives, first we need to identify load forces and moments using main variables such as design variable, which also means the material density, the design objective or weight reduction, and design constraints such as the volume and the shape. Second, Fusion 360 should be used for modeling and simulations. So we will be revolving around Autodesk Fusion 360. And third is to perform topology optimization using sprung and unsprung weights as load cases. So for the significance of the study, lower control arms are responsible for the upward and downward motion of the wheels. Vertical alignment of the wheels is assured by proper functioning lower control arms. Most commercially available control arms were made fast without focusing on weight, volume, and design optimization because creating control arms shouldn't be difficult, right? But there is an importance why we should topologically optimize lower control arms. Less weight, more fuel-efficient car. And finite element analysis will lessen manufacturing costs by volume and weight reduction, like I said. And this study can help other researchers with the correlation of finite element analysis and topology optimization. Okay, for the last part, the scope and limitation, this study focuses on lower control arm topology optimization using finite element analysis. New lower control arm designs will only be based on the commercially available design from Toyota Via Sedan, which is commercially available in the Philippines. In simulating the two load cases, only sprung and unsprung load cases will be used. Sprung weight only includes the chassis, the body frame, engine, and other stock accessories without passengers and other non-stock accessories. Unsprung weight will not include any weight resting on the springs. Only forces applicable on the flat terrain will be used. So any forces that will be applied to the suspension system, let's say on a city driving, those are the conditions available on that certain type of terrain will be only used. Modeling and simulation testing are limited to using Autodesk Fusion 360 and no other simulation softwares. Topology optimization of lower control arm will only involve shape optimization, weight, and volume reduction. And for the whole lower control arm, we will only consider static structural analysis because a lower control arm is rigid and actual control arms are made out of steel. So that's it for Chapter 1. Again, my name is Brian Jones Monteverde. Thank you.
My name is Manuel Antonio F. Pradia, and I will be reporting about review of related literature. Our first RRL is the analysis and optimization of lower control arm. The main objective of this paper is to analyze and optimize the lower control arm using finite element analysis. The CAD model of the lower control arm is done in a CAD software called CATIA V5, while the static analysis is carried out in radios by Altair HyperWorks. In this paper, the application of topology optimization is done for weight reduction. Cost analysis was also performed in this study for both existing and optimized design in order to know the cost effectiveness. These are the results for von Mises stress and total deformation in this study. In the first picture, it is seen that the stress of the optimized design is greater compared to the existing design. In the second picture, it is seen that the total deformation for the optimized design of the lower control arm is less than the existing design. And based on the results, the design is safe since the values are within the permissible limits. For the weight reduction, it is stated that the weight is reduced by 15.39% because it changed from 2.6042 kilograms to 2.203 kilograms. Our second RRL is design optimization of a lower control arm of suspension system in a LCV by using topological approach. The main objectives of this study are to optimize the lower control arm for weight reduction up to 15 to 20%, to perform static structural analysis on existing model of the lower control arm using finite element analysis, to carry out topology optimization using OptiStruct Solver, to compare the factor of safety for both existing and optimized design and ensure to keep the factor of safety of the optimized design, and lastly, to perform experimentation on the physical model of the lower control arm. There are three parameters used in this paper, which are the design variable, design objective, and the design constraints. The objective is to minimize the volume of the material or simply to reduce the weight. For the constraint, the von Mises stress should be less than 620 MPa, and the design variable used in this study is the density of each element in the design space. Static analysis is performed for both existing and modified design by experimental and finite element method. A universal testing machine is also used to test the tensile strength and compressive strength of the material and also to verify the stress and deflection values of the lower control arm. The methods used for static analysis in this paper are experimental and finite element analysis method. This table shown is the result of this study. It is seen that the stress and deflection value for the optimized design is greater for both tests. Also, the values are within the permissible limits, which means that the design is safe. The mass reduced is also 17.5% since the weight changed from 1.20 kilograms to 0.99 kilograms. The factor of safety was also kept for the optimized design, and the objective of weight reduction and cost reduction has been achieved in this study. Our third RRL is finite element analysis and topology optimization of lower arm of double wishbone suspension using radios and OptiStruct. The main objective of this paper is to perform static and modal analysis of lower control arm using different materials and also to perform topology optimization for achieving weight reduction. The processes that was performed in this study in order to achieve the objective are to determine the forces that acts on the lower control arm during various running conditions, to create a CAD model for the lower control arm, to determine the von Mises stress and total deformation, to determine the natural frequencies and corresponding mode shapes, to compare the design parameters, total deformation, natural frequencies, and mode shapes for different materials, and lastly, to perform topology optimization. The CAD model was designed in Pro-Engineer software, while the calculated force and boundary conditions were applied on the meshed model in HyperMesh software. The static and modal analysis was also performed using radio software, and the main objective of modal analysis is to determine the natural motions of a system and the frequencies at those motions that occur. The OptiStruct module was also used for the topology optimization. This photo shown is the result of this study after performing static analysis, modal analysis, and topology optimization. There are two materials used in this study, specifically aluminum alloy for the existing design and mild steel for the optimized design. The values that were obtained for von Mises stress and maximum displacement are less than the safe limit, which means that the design is safe. Based on the results, it is seen that the aluminum alloy is better when it comes to strain basis, while mild steel is better for strain basis. Modes and mode shapes of lower control arm contingent on material properties, which means change in material leads to change in resonance condition. Modes are used as a simple and efficient means of characterizing resonant vibration. Optimization has several advantages since it reduces weight, product design cycle time, and cost. Our fourth RRL is topology and classical shape optimization of a lower control arm. The main objective of this paper is to be able to design a lower control arm for a sports utility vehicle. There are also 4 worst load cases that were identified in this study, specifically pothole load, one-side bump load, combined brake and cornering load, and curb impact load. A methodology based on finite element analysis was performed in this study in order to design the lower control arm, and an optimization software called OptiStruct was utilized in order to execute topology optimization. A homogenization method was also used to obtain the design topologies. Shape optimization was also performed in this study using a direct linearization method and shape vectors. It was carried out using MSC Nastran 2004 solver. These are the 3 models of the lower control arm, starting from the designing of the model until shape optimization. The first picture is the bulky model of the lower control arm, which shows the designer all the available design space, while the second picture is the result of the topology optimization. The last picture was the model used for shape optimization in this study. This is the result of every load cases in this study. It is seen that the maximum stresses for all load cases are within the acceptable limit of 225 MPa. Also, the maximum deflections are also within the acceptable range. The weight of the lower control arm was reduced from 10.34 kilograms to 9.504 kilogram, which is 8.08% reduction. Based on the results above, it is clear that topology and shape optimization techniques can be effectively used to design a lower control arm. Our fifth RRL is the structural optimization of control arm for weight reduction and improved performance. In this paper, static and torsional analysis was performed in order to improve the stiffness of the material and also for weight reduction of the component. It also deals with calculation and modeling of various forces that acts on the lower control arm. Finite element analysis has been used for static analysis and topology optimization, which involves linear solver method. The CAD model of the lower control arm is designed in CATIA V5 and imported to Altair HyperWorks for meshing. Linear static analysis and normal mode analysis was performed using radios in order to validate the design. There are 2 load cases in this paper, and these are the results for von Mises stress and deformation. In the first picture, it is seen that the values are below the yield point of aluminum. which means that the design is safe for both load cases. In the second picture, the results showed that the displacement for both load cases are below 1 millimeter, and it is acceptable since it is within the range. For the weight reduction, it is seen that the weight of the lower control arm has been reduced from 19.62 kilograms to 11.42 kilograms, which means that 41% of the weight is reduced from the base model and it becomes more stiffer. In this paper, topology optimization approach is presented to create an innovative design of an engine mount bracket. The weight reduction of control arm is taken under the consideration without varying the performance of the component. Final comparison in terms of weight and component performance illustrates the structural optimization techniques are effective to produce higher quality of products at a lower cost.
I'm Emi Eder Aliano, and I will be discussing Chapter 3, Theoretical Considerations. So in our thesis, there will be two simulations. One is the topology optimization, and the second is the finite element analysis. So topology optimization is defined as finding out the best possible solution to the problem, in which is to reduce the weight of the structure without compromising the intended performance. So let's say in here, the structure, this is the original structure over here. Then by adding the load or constraints to the part of the structure, it will give you results of being the structure optimized. As you can see here, with lessening the phases of the structure, it can help to reduce the weight, but still when it comes to the performance, they can still able to do it as well, since topology optimization is purpose to find the optimal layout for structure within a specified region. So next is finite element analysis. So finite element analysis is a simulation that uses a computational technique used to obtain the approximate solutions of boundary value problems in engineering. It is widely implemented by the automotive industry as a productive tool for design engineers to reduce both development time and cost. It's a simulation that helps to determine the reaction when it comes to stress upon an object, analyze the effect of vibrations, fatigue, and heat transfer. So next, boundary conditions. So for the simulation, we need boundary conditions in order to know how much force is being exerted to a specific point of the lower control arm. So the first equation is the weight of the vehicle acting at the center of gravity. So in order to get the center of gravity, we need the gross vehicle weight, and we'll just multiply with the gravity, which is 9.81 meters per second square. Next, center of gravity distance from front axle center line. So in order to get the S1, or the distance between center of gravity and front axle, we need the rear wheel vehicle weight, the gross vehicle weight, and the wheelbase. Now for distance of center of gravity above the ground, in order to get H, or the distance of center of gravity above the ground, we need the wheelbase, wheelbase, added weight on front wheels, distance vehicle was raised, and the gross vehicle weight. Now for unsprung weight. In our case, on our thesis, we have two cases, which is the sprung and unsprung. For the sprung weight, it is only equivalent to the gross vehicle weight, while for the unsprung weight, it's only 15% of the gross vehicle weight. And lastly, the forces acting on lower control arm. So forces acting on different areas of the lower control arm is to be considered in order to determine its stress analysis. So we don't know if the force is acting on the z-axis, y-axis, or x-axis. So different points like point P, Q, F, G, or any of the points of the lower control arm, or even the suspension system, we don't know what the forces are acting in. So in order to determine it, we'll be using the equilibrium equation mechanics in order to know the reaction forces acting on the lower control arm. So this ends on my discussion for Chapter 3.
Good day, everyone. I am Clifford de la Cruz, and I'll be presenting the Chapter 4. Chapter 4 is all about the methodology of the whole paper. The process of optimizing the topological design of the lower control arm for sedan vehicle using Autodesk Fusion 360's computer-aided engineering function is the main precision to be done in here. So here's the flowchart, and it will be divided into two phases. The first phase includes the creation of 3D model of existing design for lower control arm and carrying out its finite element analysis using static stress simulation. For the second phase, this includes the rest of the flowchart, which is mainly about the design optimization. Various parameters shall be defined and multiple cases shall be presented. So in here, we have to define first the loads acting on control arm and constrain the boundaries, create meshing on thread control arm, apply topology optimization, such as shape optimization or weight reduction, and export it to static stress analysis to carry out finite element analysis. When we have the results for both existing 3D model control arm and the topology optimized model, we can now compare them and know if the results are significant enough to say that the new model are fully optimized or within the acceptable range of values for these four parameters: the weight reduction, maximum deformation, permissible stress, and safety factor. If not, you have to go back to apply topology optimization and modify its design. And if yes, you can now go to data analysis and conclusions. For the existing lower control arm, we have here the model of Toyota Vios 2017 with a dimensions of 540 millimeters in its length, 330 millimeters for its width, and 130 millimeters for its thickness. So what does a lower control arm do? Basically, it attaches suspension members to the chassis and directs the movement of the wheels for synchronization of the body of the vehicle. So primarily, it's just a component of the car that connects the suspension system to the body of the car. So for the mechanical properties of the material, which is high strength steel, we have the yield strength with a value of 415 MPa, megapascals. This property of the material is very important to know by the researchers because it gives us the basis when obtaining the limiting stress value of the component after conducting the static stress analysis. Meaning, after getting the results, we have to ensure that the stress induced on the material will not be greater than 415 MPa. So when modeling the topology optimized lower control arm, three variables shall be considered: the meshing, boundary conditions, and load conditions. The first part in creating the design before it undergoes a simulation is called meshing. Mesh generation is a process of creating mesh, a continuous subdivision of geometric spaces into a definite and topological cells. In Fusion 360, mesh generation is automatically generated to duplicate the geometry of the domain object, including its small and intricate parts. So in here, the figure here is the mesh geometry of the lower control arm. For the next two parameters, we have the boundary and load conditions. The boundary conditions are the loads applied to the control arm and its supports. Since the modeled lower control arm has three different bolt holes, the hole A, B, and C, certain constraints and structural loads shall be set based on the computed forces and reactions present on it when connected to stop axle. So these computations for the values here can be properly seen and presented on Appendix E. So from the diagram, hole C is connected to the ball joint of the steering knuckle where it is moving only in a vertical direction as to why it is fixed in X and Y direction. Both holes A and B are connected to the frame of the vehicle, but hole A is fixed in X and Y direction because it serves as a rubber bushing with flexible mounting that allows minimal movement on the suspension system, while hole B is fixed in Z direction but is allowed to have a minimal rotary movement in X direction. So there on the diagram, which can be clearly seen the uh, loads present and its constraint. So here, this is the tabulated form for the boundary and load conditions to be applied on lower control arm. Also, the type of loads, its values and directions are considered to be the case where maximum induced force and moments are present. For this paper, two cases shall be analyzed based on a relevant scenario that the vehicle is experiencing, the sprung and unsprung mass. So what are their difference? Sprung weight is basically the majority of the weight of the vehicle supported by suspension springs that includes the weights of the chassis, motor, transmission, body, and interior, but not the passengers or the cargo. On the other hand, unsprung weight moves up and down with the wheels when traveling over a bump, pothole, and other road obstruction. This includes the weight of the wheels, tires, brake assemblies, drive axles, or basically anything directed to the suspension system or the wheels. So what is its importance? The sprung mass. Since unsprung mass only takes place if there's a bump or pothole which induces impact load, it causes the bolt holes to rotate slightly. Thus, a moment type of load shall be considered. So in here from the table, we can see that the case 1 is for sprung mass with a type of load such as force bearing force, And for case 2, for the unsprung mass, the type of loads present are moment, bearing, and moment. So here, for the first half of the simulation process, shape optimization shall be done. This simulation study will help the researchers determine critical load paths in the design and to make more informed design decision on the material removal. So first, we have the first step is to create sketch of 3D model of the object, export the model from design workspace to simulation study workspace, set structural loads and constraints. These constraints are the ones discussed previously. Define shape optimization preserved regions. So what are these preserved regions? Preserved region feature in Autodesk Fusion 360 lets the designer to hide certain parts of the object being subjected to testing from the shape optimization process. Any area that lies within these regions shall remain intact and untouched when the optimization applies. For our design, the three cylindrical bolt holes should be preserved because this is where the loads would be applied. So the next is to solve shape optimization study, promote mesh and create mesh section sketch, use offset in a sketch and create an extrude cut, and lastly is to use fillet for polishing of the material. On the second half, we have the static stress analysis simulation. So the first thing to do is to export the working model from the shape optimization workspace to static stress simulation workspace. And select simulation study material, which is in here is the high strength steel. Define structural loads and constraints, the ones previously discussed. Generate automatic contacts. So again, automatic contacts uh, feature in Fusion 360 ensures all components of the model are intact with each other. Like for example, the three bolt holes pins are made sure to be connected on the body of the lower control arm so that when simulation is applied or begin, the whole object is considered as one. Next is to solve static stress simulation study, clone a simulation model and perform modifications on the design. This is only done when the results of the study is not good, and also for our paper, three different models or designs shall be made. Kaya that's why we have to perform modifications on the design to have three different models, and also solve again static stress simulation study and compare the results. So here, for the design matrix, this is the output table. Three different models or designs shall be created and tested by the researchers in analyzing the best optimized design for a flat terrain setting in both sprung and unsprung mass. Same loads and constraints shall be applied to all the three designs to have a baseline when comparing results. The four parameters involved in analyzation of results are to be contrasted with each other in finding the best model for the lower control arm. So these four parameters are the deformation, yield stress, safety factor, and percent weight reduction. The actual model simulation results will determine the ranges of values needed in creating the design matrix evaluation. So after getting the results for these three designs, the researchers would now be able to determine the ideal ranges of values for these four parameters in determining the best optimized design for lower control arm. So for the appendices, first we have the Gantt chart. This is the projected timeline of our project. First, the appointment of topic for the May, the determination of automotive part, that's the lower control arm, facts, figures, literature gathering around May to June, preliminary simulations by the end of June. Of course, the researchers have to try first the Fusion 360 in conducting its simulations. Thesis 1 defense here in July, creating of new design models, of course, in July also, July to August, testing and simulation, same thing. This is two progress report on the end of July. For the data analysis and conclusion, it's for the August to September. That's also where the final draft writing. And last, for the thesis 3 defense is around October to November. Next, for the budget proposal, we only have two expenses: the training in Coursera Autodesk Fusion 360 online workshop, around 39 US dollars, which is 2,000 peso when converted in Philippine peso, and the printing of this paper around 500, having a total of 2,500 pesos.
So Appendix E, solutions for applied forces. So the model we chose is the Toyota Vios 2017, and then the GVWR of the Toyota is 1,500 kilograms, and then added weight on front wheels is 7.73 kilogram, the wheelbase 2,550 millimeters, and the rear wheel vehicle weight, which is 500 kilograms. So for case 1, the sprung mass, to be able to compute S1, the distance from center of gravity to front axle, based from the given values we have before, we can just substitute it to the equation, and then we'll be able to get the value of S1 of 850 millimeters. Now to compute for S2, the distance from center of gravity to the rear axle is only just the difference of the wheelbase and the S1. So the value we got with S2 is 1,700 millimeters. Now before we compute for the H value, or the distance of center of gravity above the ground, we need first to compute for SRV, which is the race vehicle wheelbase. So in here we have the wheelbase and the distance vehicle was raised. So we assume that distance vehicle was raised is 100 millimeters. So in substituting it to the equation, we got the SRV value of 2,551.96 millimeters. Now we have all the required values needed to able to compute for H. We got a value of H for 335.35 millimeters. Now computing for the center of gravity, since we have already the mass, which is the GVWR, we'll only need to multiply it to the gravity, which is 9.81 meters per second square, which is 14,715 newtons for our center of gravity. Now we'll be using the equilibrium equation of mechanics to able to compute the Fx, or the force on front wheels. So in order to get Fx, we need Fc, which is already the center of gravity, and then S1 computed before over 2 times H, and then we got the value of Fx, which is 18,648.79 newtons for the two wheels of the front part of the vehicle. So in order to get only one part of one wheel, so we're just going to divide this one to 2, so we get a value of 9,324.39 newtons for one wheel. So in order to get the value of whole A and whole B, the forces acting there, we're just going to divide the Fx for one wheel, then 9,324.39 divided by 2, in order to get the forces in the whole A and B. Now, to get for the case 2, which is the unsprung mass, given the values we have here, we're just only going to times it or multiply it with only 15%. We're going to multiply by 0.15. So with this, we have a different value for the unsprung, and of course this one will be different for the unsprung mass. So that's the end of my discussion for Appendix E, and this also ends our presentation for our thesis. Thank you.